Okay, so this video is going to be about nuclear chemistry. All right, and like it says, nuclear chemistry, this is when it is not about electrons. Basically every other time when we're talking about chemistry, it is going to be this one, not about electrons. So before we get into nuclear chemistry, and we're not going to get super heavy into nuclear chemistry, but we should at least know what the nuclear notation looks like, because it looks a little bit different from just your standard notation when we're dealing with chemical reactions. And so along with the elemental symbol, right, there's two pieces of information that are present in nuclear reactions. That's going to be the mass number right here, which is protons plus neutrons, right, just like it says, and the bottom number, which is going to be the atomic number, or the number of protons, right? So that's what nuclear notation looks like, and the reason that we put those in there is because nuclear notation deals with the nuclear particles, and since protons and neutrons are all we got there, we need to keep track of them. So the nuclear particles that are generally involved in nuclear reactions are here. So alpha particles, which are essentially a helium nucleus. We have beta particles, which are pretty much electrons. We have neutrons that are neutrons. And then we have gamma, which is not actually a particle, but it's radiation. It's very high energy radiation that is released from a lot of nuclear reactions. Then we've got our four types of nuclear reaction: fission, fusion, nuclear decay, and transmutation. So we'll talk about each of those individually here. So fission, right, this is when a heavy nucleus is struck by a neutron often, and it splits into two or more smaller nuclei along with some high energy neutrons, right? And this is how a chain reaction happens, is that for every one atom you hit and is split, then more neutrons are formed to go out and collide with other atoms and continue that splitting. All right, this can be naturally occurring, but it's most commonly found on Earth anyway in nuclear reactors, right? And we'll talk about nuclear reactors a little later. Fusion, right? This is when two or more nuclei are combined to form a new, heavier nucleus. This is often naturally occurring, and this is the process found in stars like our sun. In fact, this reaction here, minus a couple steps to get to this, is essentially what's going on in the sun right now. Give us light and heat. Then there's nuclear decay. This is when unstable atoms release nuclear particles to become another more stable element. Often naturally occurring, this is a process in which unstable or radioactive elements become more stable, right? So they're just trying to get rid of some particles to have a more stable nucleus. And then last, transmutation. This is when an atom absorbs higher energy nuclear particles to form a new element, usually a heavier one. This tends to not be naturally occurring. This is the process used to create all the man-made elements, right? So the last naturally occurring element on Earth, anyway, that we have right now is uranium at number 92. All of the transuranium elements are made this way, though to be fair, or to be honest, we have found evidence that there were a few elements that were heavier than uranium that did exist naturally, but they have all decayed from through radioactive processes. So how dangerous are these particles, right? So if we look at both of these, looking at the types of radiation that you might encounter due to radioactive processes, right? Alpha particles, they will not pass through even a sheet of paper, right? So like as long as you have clothes on while you're near something that's emitting alpha particles, you're good. Like the cloth of your clothes will stop alpha particles. Beta particles are a little more energetic. They will pass through like paper or you. They can be stopped by, some thin metal sheets or boards. They can be stopped by aluminum board, things like that. X-rays and gamma rays, they're even more energetic. All right, X-rays, as you know, can pass through most of the material in your body. It can also pass through aluminum board, but not lead. Gamma rays then need some thicker lead to block them. Neutrons, though, are the real problem, right? Neutrons are really highly energetic. They'll pass through most anything. It says water and concrete here, and this is why you have water containment units in nuclear reactors and really thick concrete walls, because to block neutrons, like you need quite a bit of water, and the concrete's got to be like, I think about 8 feet thick. So like even though it says concrete will stop it, when we're talking concrete, we're talking like an 8-foot to 10 or 12-foot wall of a 12-foot thick wall of concrete, plus a tank of water on the inside just to make sure neutrons are not escaping. They're highly energetic. So this is a term that we should be familiar with when talking about nuclear reactions. Half-life. Now, this is the time it takes for half of a given amount of a radioactive material to decay. So it depends on the stability of a radioactive isotope. It can vary widely from a tiny fraction of a second to like trillions of years, right? And that's like trillions with a T, right? Like 1,000 billions. So there are some elements that their half-life is many trillions of years. When you think about the fact that like our planet has only been here for about 4 billion years, right? So there are some elements that are radioactive, but it takes them longer than our planet has been here to decay for even half their given amount. And this goes along with nuclear stability, right? If you look here, right, the color black being very stable on this diagram, we start out at the bottom here, right, with things being pretty stable and this like nice linear progression as we have the stability of atoms. So for like a 1-to-1 ratio of protons to neutrons. But after you get to about number 20, right, you look, it breaks off from being linear and you start getting this curve going up. And so the ratio of protons to neutrons, right, has to change. You start needing more protons, right, or sorry, neutrons for every 1 proton. And so eventually you get to the point where like nothing is stable anymore. So after a certain point, everything is radioactive, right? It's right around element 80. That everything after that point is somewhat radioactive. However, you do have these spots in here where like some elements have, 10 to the 12 years for their half-life, which 10 to the 12 is a trillion. Most of the time, when you get outside that 1-to-1 ratio down here, right, things are not stable. You get up here, it's a little further out, they're not stable. And at 1-to-1 up here, right, nothing is stable. So we've got all this stability going on here that's going to depend on the ratio. So now we'll take a look at a little bit of how nuclear reactors work. All right, so the nuclear reactor, the main job is basically just to control the nuclear fission process, right? Because we don't want it to go crazy. We'll have a meltdown, very bad. So we want to control the nuclear fission process and give it a place that all that radiation is not going to be leaking out. Right? Most reactors use uranium. It's processed into small pellets, and they're stacked together in metal tubes that they call rods. And a reactor core is typically made up of a couple hundred assemblies that are made of many rods. And so in these reactors, the fuel rods are placed in water, right? It acts to both cool and it acts to slow down the nuclear process by slowing down the neutrons that are produced during fission. If you remember back earlier in this video, we said that during fission, neutrons are always produced. So it lets enough neutrons through to sustain the chain reaction, but not enough so that it runs away. Control rods, they can also be inserted into the reactor to reduce the reaction rate by absorbing neutrons. And then how we really produce electricity from this is the heat that's caused by the fission. It turns water into steam, and that steam turns a turbine, just like any other like water electricity generating plant. So this is really how a chain reaction works. I've talked about this a couple times already, that a neutron hits a large atom, it splits, releasing more neutrons. Those neutrons collide with other atoms that in turn split and release more neutrons, on and on. Chain reaction. So this is a picture of what I was talking about before with the reactors, where you've got your reactor rods here. Maybe I'll just put this in a different color. But you've got the rods here. They're in this reaction vessel. Like you've got your concrete here enclosing this. And what happens is this water gets heated really hot and pushed through this coil. And on the outside, you've got other water coming in that turns into steam. And the steam comes up through here, drives this turbine, and it makes electricity. Right? So this water that's coming in from the outside theoretically never comes in contact with anything that is touching this nuclear material, right? So, you know, in theory, like none of that radioactivity should be transferred. In reality, maybe some of it is transferred. But this is the basic structure of how a nuclear reactor works. I think about 60 to 70% of the reactors in the United States are pressurized water reactors. There's another type of water reactor that makes up, most of the other 30 to 35% of the reactors in the U.S. And just a cool thing about these reactors is this thing called Cherenkov radiation. And basically that like crazy blue glow you see in pictures of nuclear reactors, it's real. Like it's a real thing. And how it occurs is those neutrons are traveling really fast when they're released. And when they're traveling through water, they're actually traveling faster than the speed of light in water, right? But you have to remember that's really important, the speed of light in water, because nothing can travel faster than the speed of light in a vacuum. Turns out things can travel faster than the speed of light in different media like water. And so these neutrons traveling faster than the speed of light in water actually send out this kind of shock wave behind them, like a sonic boom that's created when you break the sound barrier. And that wave that's traveling behind them, we actually see as a blue glow. So kind of cool stuff that goes along with nuclear reactors. So to wrap things up, things to remember from this, the nuclear reactions, they deal with the particles of the nucleus, right, and not the electrons. So when we deal with chemical reactions, we're going to be looking at electrons. But anytime you're thinking about nuclear reactions, it's always dealing with the nucleus. Nuclear reactions pretty much always change the identity of the elements that are involved. You'll have a different element that you start with than you end up with. Whereas the chemical reactions, right, those pretty much never change the identity. The elements are the same. They may be combined with different things, but the elements stay the same. Right, radioactivity, the process where unstable nuclei become more stable by releasing those nuclear particles. And then all nuclear reactions release nuclear particles and or energy. So not all of it's overly dangerous, right? Like alpha particles, they can be blocked by cloth or a piece of paper, right? So just remember and wear your tinfoil hat to keep you safe from those mind-controlling alien beta rays. So there will be work on this, and I'll see you in class.